A ball, mass m, 1.2 kilograms, the end of a thin cord of length 0.7 meters revolves in a vertical circle about point O, as shown in the figure to the right. During the time we observe it, the only forces acting the ball are gravity and tension. The motion is circular, but not uniform, meaning that it moves in a perfect circle, a uniform circle, but it's speeding up and slowing down as it goes. Because of the force of gravity, the ball increases speed as it descends. Makes sense. Decelerates as it rises. Also makes sense. At the moment, the cord makes an angle of theta, which is 40 degrees. Below the horizontal, the ball's speed is 5.5 meters per second. At this point, determine the tangential acceleration, the radial acceleration, the tension of the tension of the cord, which is force tension. Take theta to be increasing downward as shown. All right. So normally the first thing we do is you draw a picture. Conveniently, we already have a picture here. It's really nice. So if we do a free body diagram, so we have force, I'm going to call this force centripetal going inward, but they write force tension. I'll just write force centripetal, that way I don't confuse this T, the tension, with tangential, because it's not that at all. Going inward, then we also have the force gravity going down. And what's convenient here is the diagram has already decomposed this vector for us. Actually, I'm going to draw it a little bit differently, because you can decompose it whichever one first and then add them together. So this is going to be our force gravity radial. This will be our force gravity tangential, i.e. when we take this vector, which is right here, laying it along the circle, it's going to touch in one point, and it's going to be tangential to the circle. The reason we want this is because we want to create a coordinate basis, basically the vectors, so that the vectors are perpendicular to each other, like that. That's supposed to be 90 degrees. It just makes the math easier. So what's convenient is they said that they gave us the value as mg sine theta, mg cosine theta. Now you can find that on your own. You can do it either through geometry, or you can look at the extreme case where if theta was 0, this would be fg, so it's like this. That's the circle, that's the theta straight over, force gravity tangential would be straight down, and then force gravity radial would be out. And in this case, it would all be 100% tangential, because force gravity straight down, force tangential straight down, and the way you get theta equals 0 to be equal to 1, or 100%, is with cosine theta. So that's how you can reason it out, by looking at extremes and kind of bypassing a lot of these geometry. I'm just terrible at geometry, and I just fake it a lot of time. Okay, so here's our setup. This is where the picture came from. This is where we're going to go. So we're going to start by looking at these forces. So I'm going to say that force gravity tangential, which is this component right here, is mg cosine of theta. And we're trying to find the tangential acceleration, so it's going to be equal mass times acceleration. So this is the sum of all forces in the tangential direction. We only have one force in the tangential direction, because really here we only have three forces. We have force gravity tangential, force gravity radial, which is one force but is broken up into two components. And then we have force tension here, which is always going to be radial. So we have sum of all forces in the tangential direction. That's why I have that T there for. I know it gets kind of confusing because they use that T. I'm going to write that as C for centripetal, but you get the idea. So that's going to be force gravity tangential, which is going to be mg cosine theta, which we're given there, or we can drive on our own, which is going to be mass times acceleration. And I'm going to put a little T here so we know it's acceleration tangential. Therefore, acceleration tangential is going to be equal to, m's cancel, g cosine theta. Yep. Which is going to be about 9.8 times the cosine of 40 degrees. I'll do it real quick on the Wolfram. 9.8 times cosine of 40 degrees, we get 7.5. 7.5, yep, I'm good with that. Is about 7.5, and that's going to be meters per second squared. Not too bad. All right, now we want the radial component of acceleration. So sum of all forces, I can put a little r here for radial. And I'm going to say that in towards the center of the circle is positive, and outwards is negative. So I'm going to say that this is force centripetal, this force C up here, and then I'm going to say minus force gravity radial. Now really it's plus, but I don't like using negative numbers, so really it's going to be plus, and then force gravity radial is a negative number. But if I call force gravity radial positive number, then I subtract them. Worry less about the formalities and more about the concepts. So sum of all forces is going to be equal to mass times acceleration, which in this case is going to be mass times acceleration centripetal, because it's creating circular motion. And that's going to be mv squared over r. So I wrote this little AC here for centripetal acceleration. So expanding this out, we know that for centripetal, that's going to be our mystery variable that we're looking for. So rearranging this, Fc is going to be equal to mv squared over r plus our force gravity radial, which from our diagram we know is mg sine theta. And when we kind of look at this, it makes sense that they're adding to each other, because if you think about the tension on the string, the force pulling out on the string is going to create more tension. So that seems reasonable, at least not unreasonable. And let's see here. The mass is 1.2, so this is going to equal to 1.2 times. Oh, we want the radial. That's okay. We're doing part C. We'll do part C now. 1.2 times v squared, which is 5.5, all over r, which is 0.7. That's supposed to be a 0. I know I shouldn't write over like that. That's terrible. You're right. I'll fix it. 0.7 plus, and I factored out the m, so we have g, which is 9.8, times sine of 40 degrees. We can do this in Wolfram. So we'll do 1.2 times the quantity. Let's see, it's v squared, which was 5.5 squared, divided by the radius, which was 0.7, plus gravity, which was 9.8, times sine of 40 degrees. That's probably right. And it gives us 59.42. 59.42 newtons. Make sure I squared that speed real quick. Yep, I squared the speed. That looks reasonable. I'm good with that. Good with that. So now, this is going to be our answer to part C, which is our force tension, the tension of the cord. And then we want to also determine the radial acceleration. So the radial acceleration, this is going to be force, gravity, sorry. The sum of all forces, let's see here. This is going to be our radial acceleration, our acceleration centripetal. And that is going to be v squared over r. So acceleration centripetal is going to equal v squared over r, which is just going to be 5.5 squared over 0.7. So if you think about the acceleration, so we have uniform circular motion, and the radial acceleration for uniform circular motion is always going to be your centripetal acceleration, i.e. the v squared over r. Not to get too deep into the weeds here, but a vector is a magnitude and direction. And this centripetal acceleration is basically the acceleration required to change the direction of a vector, or a velocity vector. So that's the idea where it comes from. All right, so 5.5 squared over 0.7. 5.5 squared over 0.7, and that gives us 43.2. So it's going to be 43.2, and then it's going to be meters per second squared because it's an acceleration. This is the answer to part B, the radial acceleration. So the key takeaways here, just kind of back up. We have tangential acceleration going this way. We have radial acceleration pointing out from the center. We have a force due to gravity, which we can decompose into both of them. The hardest part of this problem is the geometry of getting which one's sine, which one's cosine. But that was done for us, so that was too bad. And then we just use the idea, it's Newton's second law. Sum of all forces equals mass times acceleration. When we do tangential, we just have tangential. And then when we do radial, we have centripetal, mass times acceleration centripetal, which is mv squared over r, and we just kind of work from there. So hope that helped. See you next time.